And as Avi noticed, I actually plan on writing on the board. So this leaves you with time to ask questions. Do that as much as possible. For most of the talk, I will discuss algorithms for graph coloring, but I want to begin with a few minutes about exact algorithms for NP-complete problems in general, just to give some motivation and background for why do we do this. So first of all, the obvious thing to state is that most of us believe that NP-complete problems should not have efficient solutions. Right, and even for a lot of these problems, we believe that the best solutions should be exponential. There is always an exponential solution, as for any NP problem, you can just enumerate over the search space. But nevertheless, there are better algorithms for many, or even probably every NP-complete, almost every NP-complete problem we care about. And actually, this was known longer, a long time before even the definition of NP came up. So for example, already in, I think it was 62, there were non-trivial solutions for TSP. I think it was like Bellman and by non-trivial, I mean something like, instead of n factorial, something like 2 to the n. And yeah, as stated, this was before the definition of NP. Obviously, after the definition of NP, a lot more people cared about these things. And now maybe a good question to ask is why? Right? Why do we care about exact algorithms that are not efficient? So there are a few good reasons. I care less about the first one I'm going to state and more about the last one I'm going to state, but still I will state a few of them. Then one reason is that people actually want to solve them sometimes. Like, for example, in practice, people use a lot of things like SAT solvers and integer programming solvers, things like that. But the reason that this is not something I'm going to focus on this talk is that in practice, a lot of the things that people do are heuristics. Because in general, instances that people care about of these problems are probably much easier than the worst case thing. But I will note that this is not the case for every problem. So there are other problems that people care about actually solving, in which there is no reason to assume that the instances they want to solve are not the hard case ones. For example, I don't know, factoring, things like that. So when you're trying to factor an integer, this is kind of an adversarial thing. Usually you assume that if someone uses for cryptography, for example, some composite number, it would not be easy in some reason. And here there is a lot of difference. This is not an NP-complete problem, but there is a lot of difference between naive algorithms and algorithms that people know how to do that are still not efficient, but are practical for a much larger number of bits, for example, in this case. A different reason to care about these things is to just understand the landscape of hardness. This means, for example, we know by now that many of these problems are fixed parameter tractable. This means that if I limit some parameter, then I can solve the polynomial time. Some of these problems you can approximate the solutions to and so on. In order to understand this type of properties, we need to know something about exact solutions for them. And the last thing that I am going to talk a little bit more about, which is maybe my main reason of interest in this thing, is the attempt to, in some sense, quantify P versus NP. So we'll just write this down and we will soon understand what exactly do I mean by that. But in a sentence, my meaning is that it is quite hard to deduce some type of like fine-grained implications of P is not NP, because this just means that there are no polynomial solutions for these problems. And if we understand the exact algorithms better, we can come up with more, let's call it quantified conjectures. We have things that we have an easier time to figure things out of. And let's begin maybe with the most classical example for any NP-complete problem. Let's talk for a few seconds about SAT. So a very short reminder, what is SAT? I give you a Boolean formula and you need to find out whether or not it has a satisfying assignment. Whether or not there is a satisfying assignment to the n Boolean variables of a formula. And I will also give you a quick reminder about what K-SAT is. So K-SAT is a restricted version of SAT where we need to solve the same problem, but now the input has some special form. This is KCNF form. What is KCNF form? I have some clauses separated by AND gates, and each clause is just a set of some variables or their negations. This is called literals. This is a CNF form, and the KCNF form is the case in which each clause is of size at most k. So obviously SAT is NP-complete. This is the first problem we knew was NP-complete, and K-SAT is polynomial for the case of k equals 2. And then NP-complete for any larger. So this we should all be familiar with, but now we can ask ourselves, how fast can we solve SAT? Yeah, so this is NP-complete, but still I might want to solve it. So for the general case of SAT, we actually don't know anything much better than the trivial solution. So I'm going to write this thing a lot of times. When I write this, maybe I will not even write this star, but when I write O star, I mean that I don't care about any factor that is sub-exponential. So the naive solution for SAT takes up to sub-exponential factors 2 to the n time. This is just enumerating over the entire search space. And we do have non-trivial algorithms that shave sub-exponential factors, but we don't know anything exponentially better than the naive 2 to the n. And we will talk about this in a few seconds.
When you say now an algorithm to find a solution means to answer the question whether there exists assignment or to find the assignment.
Okay, this is a good question. In many of these problems, this is equivalent. In SAT, for example, you can just, if you can decide if there is a solution, then you can, let's say, try both assignments to the first variable. Then you see which of them still maintains a solution, and then you start constructing a solution using that.
Up to a factor of n, right?
Yeah, up to a factor of n.
You can start discovering the bits of the, you know that an assignment exists.
Yeah.
How do you find it? You say, let's see if I set the first bit to 0. That's another formula. I just set the first bit to 0. Gives you another formula, and you ask, is this satisfiable? If the answer is yes, you proceed. If the answer is no, you must start with the 1, and that's the easy reduction.
Yes.
It's called self-reducible, and that happens with many problems.
Yeah, so like it's usually the case that the two things are equivalent. Again, as I've said, up to this maybe polynomial or some exponential thing. Okay, so we don't know anything much better than the naive solution for this. But for K-SAT, actually, we do know how to do something better. So what do we know about K-SAT? So actually, for a very long time, we know that for any fixed K, there is some epsilon that depends on K, but this is a constant. If K is a constant, such that you can solve K-SAT in 2 minus epsilon k to the n. So for any fixed k, you can solve K-SAT exponentially faster than 2 to the n. And this was, I think, that the first such result is by 83, if I'm not mistaken. There is a lot of work on improving this constants. I think it's the best one still is ours from like a year ago. This is with Hansen, Kaplan. And it is still open. What is the exact asymptotic behavior of this epsilon case? And the reason I mentioned this problem in connection with this quantifying P versus NP thing is that people, because of all of this work about exact algorithms for SAT, made several conjectures about how these things should behave. So I think this is due to Turi and Pagliazzo in 99, if I'm not mistaken. They were the first to introduce two conjectures. One of them is usually abbreviated to ETH, which is the exponential time hypothesis. This is basically saying that 3SAT takes this is basically saying that 3SAT takes exponential time. Exponential time hypothesis is just saying that you need exponential time in order to solve a K-SAT, 3SAT problem.
Less than 1.
I wrote it like this.
Minus epsilon K.
All right. Sorry. Yeah. This is just stating that you need exponential time for this. And there is also the strong exponential time hypothesis, which is the conjecture that these things should go to 0. These things should converge to 0. This means basically that SAT, like some subtlety, it means that SAT cannot be solved in general faster than the naive time. And as I said, these things are some quantification of P is different than NP, and this turned out to be very, very useful. In what sense did this turn out to be very useful? In the sense that in recent years, there are many conditional lower bounds of the form. If these things holds, then we have some very fine-grained polynomial lower bound for other problems we care about. So
maybe before the fine grain, this as it stands, it seems like it's talking only about satisfiability, but actually the paper is an amazing paper, and in it there are reductions that show that results like this impact lots of other, basically all the natural anti-complete problems you can talk about. So they are
completely,
which is
completely right.
Trivial.
Yeah, completely right. As Avi said, and the thing I wanted to put a little bit more spotlight on is like fine-grained consequences of this. But in general, there are many problems that by now we can say that if this SETH thing holds, for example, then let's say an example of this statement is that the graph diameter can't be computed in n to the 2 minus epsilon time for any epsilon larger than 0.
Cannot be computed.
Cannot be computed in this thing. Yeah, or for example, similar things for finding a pair of orthogonal vectors among a set of vectors, or many other graph problems and string problems. We can say the same for things like longest common subsequence, for edit distance. By now, we can actually also do the same for approximation algorithms. So, because we have some quantified version of P versus NP, we can get much more fine lower bounds using this. The first of this form was probably of Vasilevska, Williams, and Roditi. Virginia has a lot of work in this body of work. Also, Mirabud has probably at least half of these papers. Yes.
You know, all these cases where you get a tight lower bound polynomial, is the algorithm that gets that bound, is the trivial or easy algorithm, or is it cases where, like with STP, there's something very sophisticated, but you still get a lower bound?
Yeah, good question. I don't think I encountered something with an SDP type thing, but there are many algorithms that are not the naive ones. So the trivial ones for this, there are such lower bounds for a lot of things that depend on matrix multiplication, and in a lot of cases, this requires, like in a lot of cases, the lower bound would be what you would get if matrix multiplication is in quadratic time, things like this. I'm not aware of this type of bounds for like tight lower bounds with SDP upper bounds.
But it is a good point to stress that in many cases, it just matches the best we know.
Yes, yes.
That's polynomial time algorithm, okay?
Yes. Actually, maybe this is worth talking about next semester or something. Okay, so this is part of the reason to care about these things, and I will now erase this part because I want to start talking about graph coloring, and I want to compare it to the set case. Okay, so what do we know about graph coloring? So again, I will spend 2 minutes on just reminding you the definition. So we said that a graph is K colorable if you can color the vertices in K colors such that there is no monochromatic edge. Okay, and now we can discuss two problems. Like in general, we can define, maybe now it's more natural to do it in the other direction. The K coloring problem is given a graph and K, is this graph K colorable? You can think of it as a decision or a finding or search problem. And there is also the general coloring problem, which is you get a graph and you want to compute the chromatic number of the graph. This is the lowest K such that the graph is K colorable. So you can discuss both of these problems. And actually now the naive algorithm is much worse than it was before. Right, naively, if I want to find if a graph is K colorable, this takes K to the n times. Again, I don't care about anything sub-exponential. Why? Because I have K to the n different colorings, but actually you don't need this amount of time. It is fairly easy to see. We are going to write this down in a bit, but maybe you can think about the algorithm beforehand. It is not difficult to see that you can actually compute the chromatic number of a graph in exponential time that does not depend on n. I think that the first place this is written is by Lawler in 76. And actually there was a very, very long body of work trying to improve this exponential thing. There were conjectures for a long time that for several reasons that the upper bound should be 2 to the n, similar to SAT, and it took a lot of time together, but finally in 2008, I think it was achieved. This is by Yorkland, who spelled this thing. So the case is that actually, even though this is not the naive algorithm here, still graph coloring can be solved in 2 to the n time. You can compute the chromatic number in 2 to the n time. So in a sense, this is similar to what we've seen here. Actually, there are a bit more similarities. K coloring is again NP complete for every K which is at least 3 and polynomial for K which is 2. This is just testing if a graph is bipartite. And then the next natural question is, do we have this type of a phenomenon? Can we solve K coloring faster than graph coloring for every K? Can we solve it better than this 2 to the n? And this was not known. So like what was known is that free coloring could be solved in this amount of time. This is Eagle and Epstein. For coloring could be solved. Sorry, this is 3-3 and this is 7-3. This is Homin et al. But this was all that was known. Like for any K which is larger than 4, there was no algorithm for a K coloring faster than computing the chromatic number of a graph. We are going to give some actually only partial answer to the general case in this thing. But first of all, just to maybe start showing something algorithmic, or at least showing some of the tools for stuff, let's talk about this 3 to the n and 2 to the n algorithms.
Board you cannot.
This I can write on?
You can write on, but you cannot lift it afterwards. So if you want.
Not sure that I would want to lift it, but
ETH, kind of under ETH or something, application for coloring?
okay, so this is a very good question. A big open problem here that people did think about a lot, and there is still no lead on this, is showing that the two things are equivalent. So many of the implication of SETH you can also get from conjecturing that graph coloring takes 2 to the n time, but there are no reduction between the two things. So it is interesting to try showing that these two conjectures are equivalent.
We do 2 minus epsilon k for the example.
Yeah, that like if you can do one of them in 2 minus epsilon, we can do the other in 2 minus epsilon. This is I was talking about the general case, like this thing, like showing that general graph coloring and general sub are like either one of them can be solved exponentially faster than 2 or both of them. Okay, so let's say a few words about the algorithms. So first of all, a very general simple observation about graph coloring is that a graph is k-colorable if and only if the vertex set can be partitioned to k independent sets, right? Yes, because yes.
Everything you're talking about is deterministic, or you're allowing randomized algorithms?
Good question. We will not need randomization for almost anything. We will use it like for one of the results in the end. But everything I mentioned so far is deterministic for most of
everything is interesting also for published.
Yes, everything is still interesting, everything is still open, but I mean, when you talk about exponential algorithms, de-randomizing things is not very difficult for many of these problems. There are some problems for which it is still difficult, but you have a big toolbox to do these things. Okay, so a graph is k-colorable if and only if you can partition it to k-independent sets, because every color class is an independent set, and every independent set can be a color class. So this, for example, gives this 3 to the n algorithm quite easily. This is just a simple dynamic problem. So to get the 3 to the n, you just need to consider the following dynamic program. We want to compute the chromatic number of every induced subgraph. So for every subset of the vertex set, I would want to compute the chromatic number of that induced subgraph. And how would we do that? Then we can notice that this is just the minimum of every independent set within this vertex set. Of 1 plus the chromatic number of the rest. Right, I can just peel off independent sets, and obviously I should have, if everything is independent set, then this is 1. And so if I want to compute the chromatic number of some induced subgraph, I can peel out an independent set, say that this is a color class, and look at the smaller induced subgraph, which is the rest, and I already have its chromatic number. And the running time for this is 3 to the n. Why? Because I go over all the subsets, and then I go over all subsets of vertices, and then I look at every subset of them. Right, this is and the first methods in which this was improved is by saying things like I don't actually need to consider all independent sets, but something like only maximal independent sets, and so on until this 2 to the n improvement. We will now see. I should just use this code, I think. Okay, so now I want to talk about the 2 to the n algorithm, but first let me introduce some old tool we will need for this. So this is something people calling it the zeta transform. So other people calling it the first Möbius transform. Depends in the US. But let's say I have some function from any power set. So you can think of this as the real numbers, but it can be any ring. So I have some function from a power set to any ring. I can define f(x) to be another function from the power set to the same ring, defined by f(x) of a subset is the sum over all subsets of this subset of the original function. Right, so if I have the entire function f, then how fast can I compute this entire function f hat?
The size of x. So what?
It's like naively, you can do it in the same time as before. If I want to compute all values of f, it will take me the same type of running time, but actually already in 37, Yates showed that you can do this in roughly 2 to the n time. And so this can be done in n to the n. So this is roughly 2 to the n time, and let's see how you do that. And this is also not very complicated. Can people still see this article? Okay, so we're going to compute a sequence of functions. The 0 function is just f, and we'll compute f1, f2, up to fn, such that fn will be what we want to compute. And the way we do that is by defining fi of x to be. So, okay, I need some order over my elements, so let's call my elements 1 to n, because why not? N is the number of elements. Let's call my elements 1 to n. So I will have 2 cases. The first case is if I is within my subset, then fi of x will be defined as fi minus 1 of x plus fi minus 1 of x without that I, and otherwise it will be just fi minus 1 of x. Okay, so what did I do here? So basically what I did in the ith iteration of this thing, obviously this is something I can compute in time that is just 2 to the n. This is just either adding 2 things or copying a thing from the previous function. But what I did here was basically taking one coordinate of the hypercube and adding everything that is 0 on this coordinate to everything that is 1 in this coordinate. So maybe we can show it by drawing. This is a simple induction. I have this type of cube. So we have our hypercube, and then we go over the coordinates 1 by 1. And for each coordinate, what we are doing is basically to take the 0 half of the hypercube and add it to the 1 half of the hypercube. With several colors. And this means that, for example, after the ith iteration in fi, what am I going to have for a subset x? Then this will be the sum of all of the subsets of x that are the same as x and all of the coordinates after the ith coordinate. So in the end, I'm just getting this f hat. So this is now we know that we can compute this thing. We are going to use it soon. Okay, so this is basically the only tool we need in order to show this 2 to the n algorithm that is very simple. It uses a clever trick, but the algorithm itself is very simple. So this is what they do. They are basically saying the following thing. Let's define by I of some induced subgraph the number of independent sets in this induced subgraph. And the first thing we need to notice is that we can compute this thing for every subset efficiently. Why efficiently? In the sense that we can do it in 2 to the n and not 3 to the n. How come? Because of what that is. Sorry. Oh, okay. So I will define I of some subgraph of my graph, induced subgraph of my graph, the number of independent sets that are in this induced subgraph. Okay, and my claim is that we can compute this thing, compute all values. Roughly 2 to the n time. How come? Because of what we just saw. Right, so very easily we can compute the indicator function of whether or not something is an independent set. Right, we can, let's call it like this. This is just is X an independent set. This takes only 2 to the n time to compute. This is just go over all subsets and check if they are independent sets or not. And the function we see above, this I, this abuse notation.
X is a subset of vertices.
Yes.
Just check if it's
Why do they include that? Just to
because you have to check.
Yeah, I want to compute it for all values of
For all values,
X.
okay,
Yeah,
very
I want to say that you can compute this for all subsets of vertices in 2 to the n time. And then the number of independent sets in an induced subgraph is just the zeta transform of this thing. And actually this quantity can be computed even like using a more simple dynamic program type of thing. If I want to compute this for all subgraphs, but we use this transform for more things afterwards. So let's do it in a more unified way. Okay, so I can compute this for all values of, I can do this for all values of X. And now let's look at the following quantity. So given any graph, I can compute the following thing. I go over all subsets of vertices. And I want to write the following thing. Okay, what did I write here?
K is the size of the bit.
K is the K from the K color. I want to check if a graph is K colorable. Then what I will do is to compute this sum. I go over all subsets of vertices. I take some sign that depends on the parity of the size of the subset of vertices. And is can even ignore this. Maybe we'll get -1 of what we want, but it doesn't matter. It's just the parity of V prime times the number of independent sets in the induced subgraph on V prime to the kth power. So obviously this can be computed in 2 to the n time. And what we are now going to claim that this is in fact just an inclusion-exclusion formula for the number of K tuples of independent set in the graph that cover all vertices. Okay, so why is that? So here is maybe the basis of any inclusion-exclusion type formula. If I go over all subsets that are between two subsets, S1 and S2, yeah, let's assume that S1 contains S2, and I go over all subsets between them, and I sum up the sign of what I get, and I have two options. This is going to be either 0 if S1 is not exactly S2, or the sign of either S1 or S2 if they are equal. Why is that? Because if there is anything in S2 minus S1, then there is like a bijection between odd things and even things. I take all sets with that thing and all sets without that thing. There is a bijection between them, so every odd and even thing will cancel each other. If the two sets are the same, then this is just one thing. I sum just over the sign of that one thing. So what am I going to see here? Okay, so what actually are we summing over? We are summing over K tuples of independent sets, right? If I take the number of independent sets in some subsets to the K power, I can think of this as a sum of weighted K tuples I1 to Ik of independent sets in the graph. And now we can ask ourselves with what weight each K tuple of independent sets is going to be counted in this thing. So a specific K tuple like this is counted for which V primes. So which subsets will include this K tuple of independent sets. So this will be anything that is at least containing all of them, right? If I want to have this thing counted in these K tuples, I need to contain all of the vertices that these independent sets are using. And yeah, this is all the way of like being. So each such K tuple is counted in all of these things, but as we see here, it means that if this union of the independent sets is not exactly my entire vertex set, then they are going to cancel each other, because I will count it with an even sign, the same time as I will count it with an odd sign. So actually what I'm counting here is just the number of ordered K tuples of independent sets that cover the entire graph. Right, so this quantity is going to be 0 if the graph is not K-colorable and larger than 0 if it is. Okay, so again, fairly simple, but like a clever trick that is actually useful for a lot of other partition problems. Using the same trick, you can kind of get a 2 to the n algorithm for any problem of partitioning your graph to things. Okay.
I have a question that is
Yes.
related. So you said, so this is the fast zeta transform because you're adding up everything, right? And what you're doing here is a Mobius transform, actually, right? It's
Yeah.
the inverse of the zeta transform. So
Yes.
is there an actual version of the fast Mobius transform for this process?
Yeah, so actually like the inverse of what we defined here is indeed.
Yeah, so the question is, can you also do the Mobius transform in time?
Can you do the inverse of this or the Mobius transform for
Time 2 to the n? Because here you're only computing the end point of the Mobius, right? You're just computing the
yes.
Mobius on 0, 1, right?
So if you consider the function that just negates every entry, negates every odd entry, I'm sorry, let's say that.
Yeah, no, sure. So the question is, instead of you just said from f you can compute f hat in time exponential.
Yeah, so you're wondering if I can do the other direction.
Yeah, if I give you f hat, can you compute the f in time exponential?
Yeah, so this is what I wanted to claim. I want to claim that if you consider the transform that just negates every odd subset, this is just go over my function and add -1 to every odd entry. And then if you negate every odd subset, then apply the then apply the function after the Möbius transform, and you apply f at, and then you again negate every odd subset, and what you're going to get is
All right. All right. Yeah.
yes.
Okay.
So you can
Yeah.
compute the other direction quickly as well.
Oh,
Yes.
so if we don't want to use exponential memory,
This is again a good question, and there is actually a work about this thing. Similar tricks work, but give you worse things. So like the best known algorithm with polynomial memory takes something like 2 to the 3 to the n time. So you can still do things, but we don't.
the 3 to the n didn't use it, that you told us.
The 3 to the n it doesn't need, and I'm saying that you can't get all the way to the n yet with polynomial memory, but you can get better than 3.
Ah, okay.
Yeah, you can get to something in between them. Okay. Take So finally, maybe I will try to say a bit about what our result is and what we show. Right in the corner, what we know. So we said it like for general, let's just call it making the chromatic number. This we can do in 2 to the n. For the coloring, we said something like this. For coloring, we said something like this. Okay, and I do need to define 2 more problems. So a generalization of graph coloring is something called list coloring. What is list coloring? So this is the same problem as graph coloring, but now instead of every vertex having the same possible colors, every vertex will have a list of possible colors. So this means that I have my graph, and now each vertex, instead of in the regular graph coloring, let's say free coloring, for example, you can think of every vertex as being able to choose a color between 1, 2, and 3. Then in the 3 list coloring problem, every vertex will have a set of size 3 of possible colors, but the union of all of these sets can be much larger than 3. Something like this vertex can pick one of the colors 1, 2, 3, but this one can pick one of 1, 3, 5. This can pick 1, 2, 4. This can pick 2, 4, 5. So this is a generalization of the previous thing. And there is even a further generalization of all of these problems we have seen so far that is related to Subhash's talk from yesterday. So all of these things are constraint satisfaction problems, right? So like KSAT, for example, is a constraint satisfaction problem where the alphabet is of size 2, the alphabet is binary, and every constraint includes k variables. So we call this the 2K CSP, but K coloring and K list coloring are examples for K CSP. This means that every variable is K-array, every variable has K options, but every constraint is on 2 variables. And the reason I mentioned these 2 problems, or the first reason I mentioned these 2 problems, is that these 2 algorithms are actually for K-seq 2 CSP. So both of these things also work for list coloring, and they are a bit more general than that.
For K equals 3 and 4.
Yes. Yes, and then the reason that for low Ks, the algorithms look, they are much more local. They are basically, they try to construct a coloring. And they are doing something, this is also similar to what is done in the SAT algorithms. They try to color things and rule out options by things that were colored before that. And we saw that the global algorithm is more global in a sense. It doesn't construct a coloring vertex by vertex or anything like this. So yeah, they can solve more difficult problems, but they have the caveat that the starting point is getting worse and worse because the search space is getting larger and larger. So if you try to actually color locally, probably wouldn't be able to get very far. Okay, so now we can talk about what we showed. First of all, let me define something. So we will say that a graph is alpha delta bounded if it contains at least alpha fraction of vertices that have degrees that are at most delta. So graph is alpha delta bounded if at least alpha fraction of its vertices have degrees bounded by delta. Okay, so what we are showing is the following thing. We showed that the chromatic number of a graph can be computed in 2 minus epsilon to the n for epsilon that depends on this alpha and delta. So, for example, if there are any constants alpha and delta such that your graph has at least alpha fraction of vertices of degree at most delta, then you get an exponential improvement. This, for example, includes all sparse graphs, right? Because every sparse graph has a constant fraction of vertices of bounded degree, and many other families of graphs. And we use this thing in order to show a reduction from this thing direction. What I want to say is that if you can solve k minus 2 least coloring, then you can also solve k color. So using this thing, we show a reduction from coloring a graph to a least coloring a graph with 2 less colors, and this, for example.
So it's a sub-exponential reduction.
Yeah, reduction, not even sub-exponential in terms of like less than 2 to the n. Like if you can do the first in less than 2 to the n, you can do the second in less than 2 to the n. This, for example, means that this translates to a 5 and 6 coloring also in less than 2 to the n. And in order to get these things, and this is something that is hopefully useful for other stuff, we need to introduce some new removal lemma for subsets. So this will be what I will want to discuss in the next hour mostly. So like a main ingredient or a main new ingredient in all of these things will be some new type of removal lemma for small subsets. We will soon define and see that. And yeah, okay, so I think that like the next half of the talk will be an overview of all of these things. I'm trying to think if this is still early for a break.
It's not early, it's whatever is natural.
So let's do 5 minutes because I wouldn't want to break afterwards.
So we can take 5 minutes break.
Okay, so let's take 5 minutes and then we will talk about the things in this one.
Another question. You know of other kinds of process where the transform and the Mobius transform way faster than you would expect? Like for instance, imagine the subspaces of a finite vector space.
So actually, like for the result, we did need like some like sparse version of it in a sense, which is something like saying that if I know that a lot of the outputs should be 0, then I can do something much faster because I don't look at everything.
Oh, I was not asking whether you can do it even faster than 2 to the n. I was asking something like imagine that I would look at not the, so the pole set you're looking at here is, I give you some set, is all subsets of that, right? That
Yeah.
include.
Oh, you're saying that it will be defined by a different.
Yeah, so then imagine now that I look at this pole set, which is all subspaces of a finite vector space, and it's still ordered by inclusion, right?
Yes.
You have a Zeta transform there, you have a Mobius transform there, but
That's a good question. I
the
think.
space is much larger, and I mean, if the field is not binary.
Yeah, there is the, okay, so I think like the number theoretic Mobius transform, you can also compute it quickly, and this doesn't really go over. I mean, like the entire space is different, right? You go over like things that divide.
Yeah, there's also the, you know, the pole set you're thinking now is integers with division. That's also another pole set.
Yeah, so I think that there they know how to do it.
Oh, I see. So it's not too hard to imagine that you can do faster than the naive algorithm for
Yes.
reasonably structured process.
Yes, but except of these two things, I'm not aware of more. But maybe
Yeah,
it's just like because it was
these two are very well structured, right? So here you're kind of the idea here is that you're essentially doing a phospho triangle, right? And that's the structure you're using. And you know, when you look at whole set of subspaces, you probably can do something sort of similar, not exactly the same, but sort of similar maybe. In division, I guess you would have problem with factoring, but you know, at this point you're doing exponential time, so maybe you can kind of whatever.
Yeah. I mean, like just I guess it depends on the structure. Like
Yeah. No, okay. It was more of like a curiosity question rather than.
Delete some of the pause.
This could be related to our thing. Because, well, not because that involves the Mobius transform of the finite vector spaces, right? So if you can compute it fast, you can argue that you could do the space structure hierarchy fast, or faster than the naive. But
it was possible that would extend.
Yeah, well, it's still going to be exponential in some sort of sense because just the how many subspaces you have, you're not going to beat that. Not do something stupid on top of that, right? Something slightly smart. Also, I was looking into, and it shouldn't be too hard to compute space crotchets factored by the essence. It should be. Yeah, because they're just going to be space crotchets. Now, the multiple should be some multinomial divided by some specific factorial. But the factorial is easy. Factorial is 2 to the k factorial, where k is the, not 2 to the, I'm thinking of binary alphabet. In the binary alphabet, it's 2 to the k factorial, where k is the dimension of the space that you're looking at.
Is mass transfer easier in this symmetric version?
By this point, no. So mass transfer is probably going to be even harder, but the point of doing that is that we're going
מה שאני בעיקר רוצה
trying to say here's what the project actually looks like. Trying to say here's how we get bound.
It's up to you. I don't.
It actually hurts you because
לא הסתכלתי מספיק על הזמן, אני לא יודע, עבר 5 דקות. Okay, so let's get back to it. Actually, Ronen just asked what I'm going to discuss more out of these things. So actually my main objective is going to be to present this removal lemma and to show how it is used. So we're not going to, the second part we can actually probably fully do. This is much simpler than the first part. The first part is very technical, but we will show enough overview of the first part just to be able to show how the removal lemma is used, because this is hopefully, it should give a good idea for why it is useful and in which scenarios it can be used. Okay, so let's go back to like simple observations about K color. So if I have a graph that is K colorable, then any subset of vertices, let's call it U, must contain a large independent set. What is a large independent set? Then independent set, let's call it U prime, size U prime, which is at least 1 over K fraction. Why is that? Because the biggest color class is an independent set, also the intersection of the biggest color class of whatever subset of vertices I'm looking about. Okay, so we are now going to, let's look at a simplified version. So we claim that for any alpha and delta, we are going to show an exponential improvement for graphs that are alpha delta bounded, but let's begin with a much simpler statement. I'm going to add 2 assumptions. So the first assumption that I'm going to add is that K is constant as well, right? Because I would want to be able to say that the naive thing is already large enough. So whenever I'm going to say that something is large, I mean it is of linear size. It is of size that is proportional to the number of vertices. If K is a constant, then yeah, like this is still large. And the second assumptions we are going to make, that is much more terrible than the first one, is that alpha is 1. So we're not going to start by discussing graphs that only have a fraction of vertices of bounded degree, but actually bounded degree graphs. And this is obviously not an assumption we are going to want to stick with, but this removal lemma is going to translate something from a bounded degree graph to a graph where only a fraction of the vertices is bounded. Yes.
Maybe you said it before, but if it's just bounded degree, what's the best algorithm?
So it will still be something, it will be for bounded degree graphs. Actually, yeah, for fully bounded degree graphs, it was known that you can do exponentially faster than 2 to the n.
There's some constant less than 2.
Yes, some constant less than 2, still like going to 2 as the degree goes to infinity. Yes. So the case where alpha is 1 is simpler, but we're going to see that if we're doing it the right way, then we can translate it to the more general case. Okay, so what are we going to do? Then, because of the first observation, you can always take some very large, again, large is just a linear independent set, and put it to the side visually, and then look at the rest of the graph. Right, so I have an independent set S, and I have my graph without this independent set. Now, each vertex in this independent set is not connected, obviously, to the rest of them. Maybe it's not what this circle then. The circle is the graph. This is just a bunch of unconnected vertices, but each of them has some neighborhood in my graph. Yes, so like in this case, it will be of size delta at most. So these are the neighborhoods of vertices. But now here is a general question. If I have an independent set and I have my rest of the graph, then you can consider K colorings of this part of the graph without the independent set. And the question is, when is a K coloring of this extendable to a K coloring of the entire graph? Right, so when can K coloring of this be extended to the entire graph? So actually we can classify these K colorings quite simply. Then we can notice that the K coloring of the induced subgraph on V minus S can be extended if and only if for every S in S, this neighborhood of S, let's say it's not using the full palette. Yeah. Oh, it's the palette. But yeah, so a K coloring of this portion of the graph is extendable if and only if I didn't use all K colors on any of these neighborhoods. Why is that? Because if I didn't, I can color the vertex defining this neighborhood by the color that I didn't use, or one of the colors that I didn't use, and I don't have any contradictions because this is just an independent set. And on the other hand, if it is extendable, then the color used by the vertex defining the neighborhood is obviously not used in the neighborhood. So this leads to a definition of a new problem. Right, let's call it coloring with restrictions or restricted coloring. As I give you a graph G, I give you some subsets, U1 to US, let's call them of the vertices, and I ask you, is G K colorable such that we don't use the full palette on any UI. And if we could solve this problem faster than we can solve faster than 2 to the, now let's call it n plus s in a sense, right? The size of the number of vertices plus the number of restrictions, then we would be happy. This would give us something that is exponentially faster. And this board. So something that we show, and this I will not prove because this is like the most, like this is most of the work or most of the technical work, is that this can be solved if you have 2 extra conditions. So if every UI is of size bounded by something, let's say at most delta, and the UIs are pairwise disjoint, then we can solve this in time that will be 2 to the size of the smaller graph times 2 minus epsilon that depends only on delta to the number of restrictions.
This is to the size of V of, this is
yeah, so this is the new, yeah, so
the
this,
new thing, okay.
maybe it's confusing. I should find a name. Maybe let's call it n prime. So it will be, this will be n prime, and this will be s, and n prime will be n minus the size of s in the end. All right, so if my restrictions are disjoint and are small subsets, then I pay less for each restriction. I pay less than 2 for each restriction. So if I would be able to get this type of thing with a linear S and everything will be disjoint and of a small size, then I get some improvement. And actually, this is a bit more work, but this also true for list coloring. We'll need this at some point. Okay, so without proving this, let's begin by saying why does this imply at least what we want for bounded degree graphs. So for bounded degree graph, we can have these two assumptions. So as Avi said, the assumption about the size of the neighborhoods is trivial, right? Because if all of the degrees are bounded by, let's say, delta, then also the neighborhoods of the independent sets are bounded by delta. But actually, if the graph has bounded degree, then we can find, let's call it like a two independent set. We can find a set of vertices that is of distance at least 3 from each other. How is that? So if G is, let's call it delta 1 bounded, but this is just saying that the graph is bounded degree by delta, then there is S that will be of size n over something like 1 plus delta squared, such that all neighborhoods of vertices in S are disjoint, and S is an independent set. So basically, I have an independent set that is also, it doesn't have any shared neighbors. Why is that?
Good.
Yeah, just a greedy algorithm will give you this. I take a vertex, I will add it to S, and I will remove from my graph its two neighborhoods. Everything that is a neighbor of it or a neighbor of its neighbors. Then I will take another node that I didn't remove and do the same thing. After each iteration, I removed something that is roughly the degree squared number of vertices, and then I can continue for roughly this amount of time and get a set of nodes that have distance at least 3 from one another. So I get this thing which gives me this thing. If delta is a constant and the graph is bounded degree by delta, then this theorem gives me an exponential improvement, right? Because then S will be a constant fraction of n. But we can notice that you can't do such a thing if only a fraction of your vertices is of bounded degree. Why is that? Because even if you have only one vertex that is connected to everyone, then there will be no disjoint neighborhoods for things. Right? So it's not enough that you have a lot of vertices of bounded degree, because it could be that everybody have a joint neighbor that are more worse than that. They get roots on the board that they can't move. Okay, so now what I want to discuss is finally the statement of this removal lemma, and then we will see how we use it. Okay. Let's call it removal lemma. Small subsets. Okay, so this is the statement. Let me write it and then we can discuss it. So let's say I have script F collection of, let's call it delta subsets. These are subsets of size delta or of size at most delta. Doesn't really matter. Out of subsets. Just write subsets of what? Subsets of some universe U or script U. Right, so a collection of small, let's think of delta as a constant or as something small, I have a collection of small subsets out of some universe. And I have any parameter C, this is just a number, think of it as a very large number. It can be as large as I want. Yes.
Yeah, sorry, I just have a question about the previous, the discovery. To the end time.
Yes, so the exact same algorithm works for list coloring.
Exactly, yeah. So for this theorem, which you are not going to tell us about how it's proved,
Yes.
we can at least imagine. I mean, that this, that since you have many, you know, this sets of size delta, disjoint things.
Yeah.
You could color each of them in all, maybe in all possible ways, or at least if you could. I mean, you could color them in much less than 2 to the delta time. They are disjoint. Each one you can k-1 color in, let's say in one way, right? You can k-1 color them. If one is not k-1 color, but you can forget it, right? Because it's if only.
I'm talking about the small sets.
Small sets, yeah.
Okay. Yeah.
So you try to k-1 color them. And then you get a list coloring on the list. So here you're saving the exponent a lot for each one of them. So for their union, and the rest will be a k-1 color, a list coloring of the remaining graph. Is this some part of the idea? It's not. You don't have to.
But why is that? I mean, it could be. I mean, we will use somewhat similar ideas for afterwards for like the reduction to list coloring, but these things are not necessarily connected to everything. It could be that each one of these small subsets is just an independent set itself. So you get nothing from trying to color it. All possible colorings are possible.
All possible, okay.
Yeah.
So it's because you have to try all possible, maybe. Okay,
Yeah, I mean, you don't know.
Okay, good. Yeah, I was just wondering. Okay, very good.
Okay. So let's say I have some collection of delta subsets of some universe. This is the underlying set from which my subsets are taken. Then there is always a sub-collection script f prime and a subset of the universe q prime such that the two following conditions hold. So the first condition I want will be that for every two sets from the sub-collection f prime, the intersection of f1 and f2 is fully within u prime. We should think of this as saying that if I would remove u prime from the universe and from every subset that contains them, then f prime would be fully pairwise disjoint. Right, so this basically says that if I remove this part of the universe, then this subset is pairwise disjoint. And now the second condition we would want would be to say that this is very, very small and that this is very, very large. Right, so the exact statement is the following. The size of the sub-collection is at least, let's call it some function of delta MC, or of delta MC. But if both of them are constant, then this is going to be a constant as well, times the size of the original collection. So f prime is going to be a constant fraction of the original collection. But we also want it to be large by factor of our choice from u prime. So f prime is also larger than c, which is an arbitrarily large constant that we picked, times u prime. Right, so this basically means that if I have some collection of small subsets in any universe, then I can delete a very small portion of the universe and get a sub-collection that is fully pairwise disjoint. Where large sub-collection means this is a constant fraction of the original collection, and a small portion of the universe means that it is small by a factor as large as I want, then the size of the collection. Okay, any questions about the statement itself? Okay, so maybe later I will discuss a bit what this function is, this thing. So afterwards, Nova, Alon, and I were
Can we, maybe see it's in a very simple case when delta is 2. So this is just a collection of pairs in the graph, right? So what you're saying is that the pairs can be either connected or disconnected in the graph. But anyways, a collection of pairs, you want to remove a constant fraction of the vertices. So
yes.
A large fraction of pairs remain, and it will be larger than
Exactly.
100 times.
Exactly.
This is easy to see. This particular.
Okay.
Is easy to see.
So the statement Avi is asking about is if I let delta be 2 and I think of my set as a graph, right? I can think of the subsets as edges and the universe as vertices of a graph. Then this statement says that if you remove a subset of the vertices, then you will have a lot of edges that are pairwise disjoint. You will have a large matching, right? So what should be the size of the matching? The size of the matching should be a constant fraction of the number of edges plus. So you can just say, okay, so yeah, plus.
So you will just remove the high degree vertices.
You will basically remove the high degree vertices.
But in this case, it's very easy to hold it straight.
Yeah, I think that the thing we should. Yeah, I mean, like this. Okay, it depends on what is the size of this set, but this will be smaller regardless, right? Because your prime is of order n, and this can be of order n squared. So it will be more interesting if your set is sparse to begin with.
Yeah, your set, with necessarily be sparse anyway.
Yeah. Okay, that's a good question, and okay, maybe I will say something about this thing. So Noga and I were looking at how small or large can this constant be afterwards, and we actually showed that it has to be quite small. So if we will have time, maybe I will say more about this, but basically this is what we know at this point. So this constant decreases exponentially with delta, but if you think of C as something that is very large, then this is quite small. And indeed, every use of this thing that I have so far will lead to like very small, though exponential improvements to things because of this type of thing. But this is somewhat a regular phenomenon in like regularity statements or things like this. So it's good to see that this is inherent. This is not just us like fucking up with them. Okay. So the first question now is, what do we do with that? How do we use this statement and this statement to go from bounded degree graphs to graphs that have only a portion of the vertices with bounded degree? So
you can use the sideboards if you want.
Yes, I don't know. Actually, do people see them? I just look at myself in the. I look at myself in the Zoom.
If not there, then it will not move by itself.
Yeah. Okay. Okay. So how do we show the same type of statement for? Now I don't want graphs that are fully bounded degree, but graphs that are only partially of bounded degree. So I want this delta alpha bounded graphs. Okay, so what we are going to do is to just try to do the same thing we did before. So we have a large subset of the vertices that have bounded degrees. We have alpha n vertices that have degrees bounded by delta. As before, and as we still assume that K is a constant at this point, we can get a very large subset of them that is also an independent set. Right, so we have large independent set S with bounded degrees. And the statement about the restricted coloring problem only required S to be an independent set. The statement about solving it required for the neighborhoods to be disjoint, but just if I want to move to this problem, it is enough that this is an independent set, and we do get the bounded degrees now because we did assume that we have enough vertices of bounded degrees, and we have a large subset of them that is an independent set.
So the thing you're going to put on the side will always come from the fraction of bounded degree vertices.
Yes, so it will come from the fraction of bounded degree vertices. And here it also needs to be a fraction 1 over k of them. Obviously, when k is large, we can't do that, but let's assume that we do. But now what the problem is that the neighborhoods might be intersecting. So this is where we're going to use this removal lemma for. Okay, so what would the removal lemma give us in these settings? So the subsets that I'm going to consider are the neighborhoods of things in S, and the universe are the vertices of the graph minus S. Right, so maybe we should write it down. The universe is going to be V minus S, and the collection is going to be the neighborhood of S or the vertex S in this subset. Okay, then what do I get from the, let's not pick C yet, we will pick C later, but what do I get from the removal lemma? I get from the removal lemma a sub-collection. What is a sub-collection? A sub-collection is basically a subset of S, right? So we get S prime, which is a sub-collection of S that is, again, of large size. It is still of linear size, and we get a subset of vertices, right? We get U prime that is within V minus S, such that the neighborhoods of things in S prime are disjoint if I ignore these things. What exactly ignoring these things mean? How can I just ignore the things? Then I can't fully ignore things, but something I can do is, for example, to enumerate over their colors. Right, so what I'm going to do is to enumerate over the color of vertices in U prime, and then solve the rest. But what is solving the rest? What am I left with after enumerating over the colors of U prime? Then actually what I have in the rest of the graph is not a coloring instance anymore, but a least coloring instance. Right, because everything I enumerated on does limit the colors that its neighbors can use. This is why the second part of the statement is crucial for this use. So I want to say that even after this enumeration, I'm still fine. And now what is going to be the radical? Going back.
And for the vertices which are not in S prime, their neighborhoods you are going to do
for.
This will help you.
Oh, so I'm going to put them, yeah, you're right. I should have said something. I'm going to put them back in the graph. Right, I'm going to think of S prime as my new S. They can go back to play with their friends, their old friends. Okay, so how much did this take me? How much did this take me? So I needed to enumerate, let's say, completely naively over the colors of vertices in U prime. Right, and then I could use this lemma to solve the rest. So how much did it cost me? So it's going to cost me something like 2 to the n minus, I'm even making it slightly worse than it should be. But this F prime is S prime. This is the size of the subset. And something that is less than 2. This is actually even a little bit better because I can also take these things off this.
But the point is that C will depend on K, and you can make this.
Yes.
To
yes. So the point is that this thing is at least, because of the second part of the statement, U prime is at least 1 over C times F. Right, this is K to the 1 over C times F prime 2 to the N minus F prime 2 minus epsilon delta to the F prime. And if I just group everything that has F prime in it, what I'm getting is I have the regular running time 2 to the N times something that will be to the power of F prime, but this is linear in N, regardless of what C I pick, as long as it is a constant. So if here I will have something that is less than 1, then I will be happy. And what exactly do I have here? So previously I did have something that is less than 1. I had this 2 minus epsilon over 2. Right, I improved for this F prime from 2 to 2 minus epsilon. But now we'll also have this factor of K to the 1 over C. But obviously I can pick a C such that this thing remains below 1. And C will be something like log K. Yeah, whatever, or a bit more, just like in the order of magnitude as log K. Just want this to remain below 1, and then
wanted the inequality in the other direction.
yes.
Want an upper bound.
Yeah. Yes, an upper bound on U is the, yeah, this is okay. So if I think of K as a constant at this point, then picking C, which is also a constant that depends on K, is enough to get this this exponential improvement here. So now we got that, and I think that what I will spend the rest of the time talking about, because we will magically somehow have more time, is how to use this thing for the reduction between graph coloring and list coloring, because this is actually, it is both simpler, so this I think we can fully do, and it also shows why this alpha delta bounded definition is much stronger than just saying that the graph is bounded degree or the graph is sparse or things like this. Yeah, but basically what I want us to keep in mind is that a graph is alpha delta bounded as long as not almost all vertices are of degrees as high as I want. Right? If there is any constant fraction that is bounded by any constant, then this would be applicable. Then the only graphs for which this is not applicable is graphs for which almost all vertices, 99% of vertices, have degrees larger than 1,000,000. Right? And any constant.
Consider using the moving box, because you cover it, whatever you write here, you will cover it. So,
yeah, you're right.
Can you first say a few words about the proof of the removal lemma? Like, at least how roughly do you choose U prime or F prime? Which one do you choose first?
Okay, so actually so first I add a proof for the removal lemma that is, not sure if it is simple or not, it gets a worse bound, it gets a bound, it's not written anymore, but like this function is much worse, but the sets that it picks are easier to understand. It just picks basically some threshold and takes everything that is not covered by more sets than this threshold, so you can get something just by using that. The proof is more.
This is really, yeah. So in the case of delta of size 2, this is really just taking all the high degree.
Yes, exactly. So in the general case, this proof turned out to be much more complicated than the other proof, but it shows that even this like simple structure is enough.
If you do that, the analysis is basically counting. I mean,
yes, it's an interesting counting, but yeah, counting. Yeah, but like to get better bounds, you need like less interesting structure or more interesting structure, something is precise. Okay, so the first thing I want to do, and this is more simple, is just to show that if you can solve k-1 least coloring in 2 minus epsilon to the n time, then you can also solve k coloring in 2 minus some other epsilon to the n time, and this is going to be deterministic even, so I'm not going to need randomization for this part to get to k-2. You would need it. Okay, and the way we show this is by making a very simple observation. So first of all, definition, a dominating set R in a graph is a subset of vertices such that any other vertex is adjacent to it. And so a subset R is called a dominating set if every vertex in my graph that is not in R is connected to at least one vertex in R. Okay, so here is a claim, lemma, whatever. So if most of my vertices in my graph, if at least 1 minus alpha fraction of the vertices in my graph, and think of alpha as a very small constant, are of high degrees. This is the complement of what we can already solve. So if most vertices in my graph are of degree that is larger than delta, think of this as a large constant and of this as a small constant, then there is a dominating set R of size most something like alpha plus 1 minus alpha times 1 plus log delta over delta.
That's greedy also.
That's not greedy. That's, I mean, we can we'll soon see how we get this. So first of all, what is the statement? If a lot of the vertices, all but a small constant fraction, are of high degree, this is a large constant, then I have a dominating set of size that is going to be a very small constant fraction of the vertices. What is this very small? So the things I didn't know anything about the degree of, I'm not going to get rid of them, but the things that I did know something about the degree of, I would need only something like ln delta over delta fraction of them in order to cover everyone. Why is that? For example, if I pick a random subset of vertices, for which I take each vertex with probability roughly ln delta over delta, right? So if I picked everyone with a peak with probability that is roughly ln delta over delta, and now we can ask ourselves for a vertex of high degree, what is the probability that we hit either this vertex or one of its neighbors? Right, so if I have some vertex that is of high degree, this is at least delta, then what is the probability that I missed everything, that I didn't hit any of these things? Then it will be something like 1 minus this probability to the number of neighbors. Right, and this is roughly 1 over delta. So what I will do, if I wanted to use randomization, I could do something like pick each vertex with this probability, then as your dominating set, take what you picked in random and everything that you didn't hit, everything that you didn't find a neighbor of. And by this claim, we know that the things that I'm not going to hit are the alpha things that I didn't know anything about the degree of, plus a 1 over delta fraction of the rest. So this is enough for this. But I did say that this can be done deterministically, but you can either believe me or ask me later, but this can be easily de-randomized using, for example, like the method of conditional expectations, for whoever this means anything to. And I do want to stress the reason that this can be easily de-randomized. The reason is that we can easily check if something is a dominating set. In a sense, this is like the essence of why this is easy to de-randomize. If you give me a subset, I can tell if I hit vertices or not. Okay, so this lemma means that if most vertices are of 5 degrees, there is a small dominating set. What could we do if there is a small dominating set? This connects to what Avi suggested earlier. If there is a small subset of the vertices that touches everything, then I could enumerate over the colors of this subset of vertices. And if I have the right colors of all of these vertices, then each other vertex can now no longer use K colors, but only K minus 1 colors, because I must have colored at least one of its neighbors. Right, so this would reduce this to K minus 1, this color. Now if every other vertex has only K minus 1 possible colors, so what will be the running time? The running time would be something like K to the size of the dominating set times the time it takes me to do list coloring for the rest. K minus 1 list coloring for the rest. And okay, all we need to know now is that because for any alpha and delta that are constant, the previous algorithm solved this exponentially faster than to do the end, then I can pick any alpha and delta you want. Right, just pick a very small alpha, a very large delta. This will be as close to 1 as you want. Right, okay, so this is maybe some demonstration of why this alpha delta boundedness is a strong definition in a sense, because otherwise it's there is a lot of structure. Almost everything is a finite thing. Yeah, I will use the board that I can move up because then maybe I'll just things, but okay. So now the question is, can I push this further? And what can I do for even to get 2 colors? So a natural suggestion would be to.
Sorry, what's the next stuff?
Yeah, so like the question is, okay, so I managed to remove 1 color. Can I do it again? Can I remove more colors? Right? Why can't I use the same type of statement? Everything is of 5 degrees. I can very easily eat neighborhoods of vertices. Why can't I just do this forever? Okay, so question. What about the K minus 2 list color? Okay, so what is the problem? It is true that by using a very similar statement to what we just said, I can easily find a small super dominating set, right? I can find a small set that hits 100 neighbors of almost every actually other vertex, right? By using the exactly same statement. What is the problem though? That it could be that in the right coloring, all of these neighbors that I hit in my small dominating set have the same color. Right, so the fact that I hit a lot of neighbors of some vertex doesn't guarantee that I got rid of more than 1 color. So this seems to be a problem, right? So let's try to think when can this happen. So I have some vertex V, and let's say that we fix some coloring of the graph. So I have some K coloring in mind. When is this problem going to appear and when is it not going to appear? So let's say that the total degree of my vertex is larger than delta, for as before, for some large constant delta. Then now we can see the following thing. If I look at the color classes of the neighbors of this vertex V, I divide the neighborhood of this vertex to the K color classes, then if there are at least 2 large color classes, then everything is going to be okay with some footnote. The footnote is that everything is going to be okay, but I'm not going to know about it.
So you mean this 2 big color classes will be used for when we pick the other vertex that are random?
Yes, I'm saying that if, for example, let's say for all vertices in some coloring, you have 2 color classes of your neighbors that are larger than some large constant, then you are happy. Because then again, a random subset of vertices is likely to hit both of them. Right, but there is again a small footnote or a big footnote. I wouldn't know that this happened, even if it did, because I don't know this coloring. So I don't know the size of the color classes. I don't know the small subset of vertices hit both of them. And also, and this is less of a footnote and more of a real note, this doesn't have to be the case. It could be that I have some vertex V that is of large degree, but almost everyone uses the same color, right? It could be that like most color classes are very small, and then there is this like huge color class. Like one color class is like very large.
Even if the coloring originally is completely balanced.
Yes, yeah, I mean, like especially after I colored some things, but also I don't want to assume that my original coloring is completely balanced. It could be that it isn't.
You could do something else if it's not balanced, because if it's very unbalanced, you can guess a small, I mean, you can sub-exponential
So it's
way of finding every.
So actually, it's still very difficult because even if I tell you, even if you don't have to find, even if I give you the smallest color class, just verifying this is very difficult. Right? If I tell you this,
enumerate over all small sets, and it's okay -1. If you know.
Yeah, but how do you check which one of them is the small color class?
You don't check. For each one, you run your algorithm on the remaining graph, and there are only few things, and you reduce K by 1.
No, this will take you more time, right? Because the number of subsets of some size is larger than 2 to the. You'd have something like 2 to the, let's say the small subset is of size R. You'll have something like 2 to the R log R times coloring the rest. Right, so this will be, you can't allow yourself to both enumerate over all small subsets and to do something that is to do
the other one, but yeah, I don't know,
yeah.
Maybe not, yeah, okay.
Yeah, no, but this is, yeah, it's a good question. There is, it's a good question. If you know that the colors are unbalanced, then you do something out of that. Yeah, it could be. Okay. So what we are going to use is that in this case, we can also gain something. What we can gain in this case, if somebody was telling me that this vertex has neighbors that should almost all of them be colored using the same color, then I could use this. Right? I could use this algorithmically. I could say something like, pick a large subset of its neighbors and contract them to a single node, say that all of them should get the same colors. So this case is fine, this case is fine, but they might be combined and I have no idea which vertices are of which type. So this is something that we need to somehow tackle. So first of all, let's stick with these 2 definitions. So now I have some large constant delta prime, and I have a much larger constant, but still a constant delta. And what I'm going to do is to call a vertex good. If in some specific K coloring I have in mind this vertex as 2 large color classes, in the sense that it has two neighbor color classes of size at least delta prime. And I will say that the vertex is bad otherwise. But what do I know about bad vertices? So for each bad vertex, I know that the large color class is of size at least delta minus k minus 1 delta prime. Right, because if it was not good, then except of one color class, all of them were smaller than delta prime. So if I pick delta to be much larger than delta prime, again, I have this thing with assuming that k is a constant as well. But if I assume that this is much larger than this, it would actually need to be something like, okay, so what I will be able to do, so here is a statement, lemma, claim, I don't know, observation. So if delta is larger than something like delta prime times k times some parameter r, some number r integer that I will later pick, maybe it means something like plus r squared or something like this, then a subset, random subset of R neighbors of bad vertex are all colored by the same color, or contractible we call it, with probability, let's say, larger than a quarter. Right, so what I want to say is that if delta is much larger than delta prime, and the much larger will depend on k and some parameter r that I can also pick, then I will have the property that r random neighbors of such a vertex are very likely to have the same color to all of them. Right, the same color with probability a quarter. Probability doesn't depend on this r or whatever. Okay, and now what I would want to do is to have some way to play between these two scenarios. So let's denote by beta the fraction of bad vertices. Right, so let's say that beta fraction of vertices in my graph are bad and the rest are good. I don't know what beta is, but let's say that this is the case. Then I claim that sometimes it will be worth it to just pick a uniformly random vertex and to assume that it is bad. When is it going to be worth it? So it is a moral claim. So the moral claim is that if, first of all, we still have the alpha fraction of vertices that are of low degrees. So let's ignore them for a second. But the moral claim is that if the probability of me picking a bad vertex times the probability of the subset of R neighbors of this vertex is larger than 2 to the minus R minus 1, then this should be worth it. Why is that? Because by contracting R vertices, I reduce the number of vertices in my graph by R minus 1. Then morally, if I manage to do so with probability that is larger than what I would get by just enumerating over them, then this should be worth it. Okay, so here is some statement, and this kind of leaves us with 3 different scenarios. Okay, so what are the 3 different scenarios that we have? One scenario is that alpha is large. By large, I mean like non-negligible, then we already know what to do. If I have any constant fraction of vertices that are of low degree, then I'm done. So let's assume that alpha is small. Okay, and now the 2 other cases are that either the number of bad vertices is small, the fraction of bad vertices is small, then we can hope that again, picking a random subset will hit 2 colors of everyone and we will be happy. And the other option that is left is that this difference is large. right? If this is small and this is large, then this is large as well. Right, so in this case, what I would want to do is to pick a random vertex and to contract its few of its neighbors. And in this case, what I would want to do is to pick a random subset of vertices and to hope for the best. What exactly would it mean to hope for the best? So now I wouldn't know if I actually managed to eat 2 colors out of everyone. And what I'm going to do is something like enumerate over colors of this hopefully dominating set or hopefully good dominating set. And only for colorings for which the rest of the vertices behave as I want, only for colorings for which I see almost no vertices that I didn't hit to color neighborhoods of, only for them, I will try to use the K-2 least coloring algorithm. Right, so it will be kind of like a 2-step enumeration. First, I pick a small subset, I enumerate over the colors of this small subset. If I see that only a small fraction of vertices didn't have 2 colors being hit, then I would enumerate over them as well and use the K-2 least coloring algorithm for the rest. And if beta minus alpha is large, then I would just want to do that. What is the problem that I'm left with? Not knowing in which case I am. Right, I don't know if beta is small or beta is large. So there are several ways to solve this. Here is maybe a way that loses a bit more than we should, but this is sub-exponential, so this is okay. One way I can solve this is to, before I start my algorithm, I can guess after how many iterations I will get to this case. Okay, actually something that is important to note here is that this is both this and this are terminal cases. By this I mean that after I decided that beta is small or decided that alpha is large, I'm not going to do anything else out of this tree. Like in this case, I just run the first algorithm. In this case, I will run the least coloring algorithm, but I'm not going to continue after each of them. So the runtime is going to look like, for some iterations, I believe that beta minus alpha is large, and then I go to one of these cases. So for example, something I can do before I start running this algorithm, I can just uniformly pick a number between 1 to n, and to decide that after this number of iterations, I'm going to assume that this is not true anymore.
Alternatively, at each iteration, you do shitat matzliach.
So this is not good. You don't want in every iteration to try both alpha
and beta.
What do you mean by that?
In each iteration, you try the first ones. I'm missing something, I guess.
Yeah, so like the problem is, okay, this one you can't always do, this you can only do here. The problem is that this one is a lot of times going to be unsuccessful in the sense that you will have no coloring for a small vertex that is extendable to a full coloring, and it's two color classes of many of the other vertices. So a lot of times, if you try to run this thing, you might end up with not succeeding to do anything, but you did spend more time than you wanted to spend.
Yeah. Okay.
The actually best thing to do is you shouldn't, so guessing this iteration in advance is fine. It gives you still like a good probability, but the right thing to do is to like have some probability of going to the other case that will be exponentially decaying in that thing. But maybe, again, the moral statement to take out of this thing, which I didn't see written anywhere, but is probably, I mean, it is well known to anybody doing randomized algorithms, is that in general, if you can always get the running time over the success probability to be smaller than something, then you can succeed in this time with, let's say, 0.99 probability. And a nice thing about this is that in each of these cases, depending on how much time you are going with the first case and not the second case, you have a very different way of getting the same ratio. Because if I'm using this case a lot, then the probability of success is decreasing more and more, but the running time is getting much quicker. Because by the time I will actually do this thing, I will be exponentially in much less vertices. But in order to be correct until now, I took an exponentially smaller probability. But if I will go with one of these cases early on, then the success probability is very large because I didn't do anything that is randomized, but the running time is exponentially large. But this ratio is always kept below something, and this is enough to get what we want.
So in the moral statement, you want to gain by a constant over r minus 1 from the
Yes, but r is a constant, so
you want, it's constant, but you want to get I see, because it's they're all constant greater than it's enough.
yes, as long as this is like a strict inequality, then because r is a constant, then you gain. Right? What Avi is saying is that basically what I'm gaining is something like this divided by this to the 1 over r. Right? Like this will be my new this will be my 2 minus epsilon. Right? So as long as everything is
a number of steps like this, then you're gaining the exponent of the
yes. Yes.
If you don't need to do a linear number of steps like this, then you gain from the other two cases.
Exactly. Exactly. So like my epsilon would be something like the minimum of like this epsilon and what we just defined as the epsilon of this case. Okay. So we're almost done. I will just maybe state some of the remaining open problems, because obviously there are remaining open problems. So maybe the most interesting thing about coloring specifically is, can we get anything without any assumptions for general K? Right, not only 5 and 6, and maybe you can get a bit more now, but the question is, should there be a maximal such K? And maybe something interesting to note about this.
Okay, for which you cannot
for which you cannot save on the general graph coloring. And something that might be interesting to note here is that for K2 CSV, this is not true. So like for K2 CSV, you can show that the running time should get worse with K. And so like this takes actually something like K to the epsilon n or something like this. Right, so for coloring and for list coloring, we know that you don't need time that goes with K, but it could be that something happens for this. Okay, so like for coloring and for list coloring, we said that regardless of K, you can solve it in 2 to the n time. So like for the more general problem of K to CSV, this is not true anymore.
Here epsilon is fixed, it's some,
yeah. So like if ETH is true, then there is some epsilon. Yeah.
So that's for every K.
Yes. Yes.
This epsilon so for every K.
Yeah. So like, it could be that something gets worse with K in this type of programs.
So it's even worse than true to the
yes, so like this is okay.
So because it's bigger than true to the end, you know that it's a different ballgame, right?
It's a completely different ballgame, but there is some chance that, I don't know, maybe you could encode CSV in a much larger coloring, so there will be like, there is a point in which it passes to, maybe you can encode it in a larger one or something like this. Okay, and okay, actually there are like a lot of questions that are not directly about coloring, but everything related to the SAT algorithms, for example, it is like still a major open problem there to understand exactly what is the asymptotic behavior of this epsilon K, is in particular this strong exponential time hypothesis conjecture, whether or not it should converge to 0 or not, and things like that. I think this might be all I wanted to say.
Thanks. Well, promise to finish on time, and it did.
Yes,
So,
this is new. We're not used to that.
Questions? Questions? No audience. No. Okay. All right. Done.
Yes.
Yeah, thanks.